Okay, most welcome all of you, and in particular, of course, Professor Anna Dreber Almenberg, this year's Tore Browaldh Lecturer. Anna is Johan Björkman Professor of Economics at the Stockholm School of Economics since not too long ago, last year, something. She is often referred to as a rising star in behavioral economics, where behavioral economics is in a very broad and multidisciplinary sense. Much of her research is on human behavior in one way or another. Much is based on experiment or some kind of experimental methodology. For example, what explains the fact that some people are at least sometimes more competitive than others? How come some are more willing to take risks? And why are some people more cooperative and pro-social, at least sometimes? Can perhaps part of that be explained by gender differences? Can they be explained by various kind of norms that we have? Can they be explained by religiosity? Maybe hormone levels? Stuff like that, and that can be measured, for example, hormone levels. You can measure spontaneous, natural variances of that over time, or you can actually modify that explicitly and see how that affects behavior. She has also done research on a wide range of other topics, such as, for example, how does our perception of the quality of wine, how does that vary with the information we get regarding the price of the wine? So that says something about the broadness of the research of Anna. Much of her work is multidisciplinary, not all, but that can be one indication of that is that she has managed to publish in top journals in many fields. For example, she has published in the American Economic Review within economics. Within natural sciences, she has published within both nature and science. In psychology, she has published in psychological science. In management, she has published in management science, and so forth. Today, as you know, she will talk about replicability and more generally the extent that we can or cannot trust scientific results. An urgent issue that many of us think of in many dimensions and with respect to many events. That, of course, we can all think of Macchiarini scandals and so forth, but perhaps the problems are much more serious than that in a sense. And in that area, of course, she has done, as you know, many important contributions that she will tell you much more about in a minute, so I will not say very much about that here. She is, besides being able to publish in sort of the best outlets and of very high quality, she has also produced a very large quantity in a quite limited amount of time. And if you just look at her, and you may be surprised if you just think of you first look at the publication list, and then you look at her, and then you may think she looks so young. And I guess the main reason for that is that she is very young, and that makes of course, maybe I have other reasons too, I don't know, but that's I guess anyway, that makes, of course, the research achievements even more impressive in a very short period of time, being able to produce very large quantity, in particular quality, and in particular of high social relevance and high social importance. So we are very happy to have you here as our Tore Browaldh speaker for 2017. So Anna Dreber Almenberg, the floor is yours.
Thank you. Thanks so much. Thanks for inviting me. Thank you for letting me give this lecture. I'm very honored. So I'm very happy to talk about this topic that I'm kind of obsessed about. So this is what we talk about at home, at work, all the time. This is what my family hears me talk about. Like, this is what I'm thinking about basically constantly, even though I do some other types of research too, but this is what I'm the most interested in right now. So can we trust scientific results? That's the theme of the next hour. And in particular, I talk about studies we've done, replication studies, and studies where we have prediction markets, where we try to estimate the reproducibility of science. So I'll be talking about my own work and other people's work, and when it's my own work, it's joined with many co-authors. So one of my key co-authors, for example, is Magnus Johannesson at the Department of Economics at Stockholm School of Economics. But there are also many others that I'll forget to mention, but I'll try to remember them here and there. Okay, so this presentation could also have been called How Forking and Low Statistical Power Has Led to Replication Crisis in Many Fields, and how we should design studies and do pre-analysis plans to solve this problem. So this is basically the take-home message of the next hour. And I'm going to talk a lot about experimental studies, but the problems I'll discuss are not just experimental, they're everywhere. But I'll mainly show you the experimental problems and how we solve them for experiments, but we have to think about how we solve them in other fields too. Not just economics, not just social sciences, but basically all sciences that have some type of quantitative data that we try to analyze. Okay, so who here believes that water has memory? Anyone? Okay, so that's a good sign, good start of the next hour. I think we're on the same page then. So many people do not think that water has memory, and many people did not think that water had memory in 1988, but Nature published a paper in 1988 claiming that water had memory. So this, of course, went against many people's priors, their kind of preconceived idea of how water works and how memory works. So they were very surprised seeing this paper coming out, and the editor, Maddox of Nature, was, I guess, also a little bit surprised. So he wrote an editorial, When to Believe the Unbelievable, about water having memory. Not very surprisingly, it turned out that water doesn't really have memory. And this took quite some time to show with new experiments, etc. Took a lot of effort and time and money by lots of people to show this. So, okay, now we know this. This was quite some time ago. But if we could have gone back in time and had some type of betting going on between scientists to elicit priors about water having memory, I'm basically wondering if we could have helped the peer review process somehow and basically said, like, okay, you happen to find something in one study, but our priors are so amazingly low that maybe we shouldn't update it so much into thinking that water actually has memory when you see it in one study. Okay, there were lots of problems with the original study, but just in general, is there some way we can kind of link betting to science, and is this useful somehow? So this is what I've been thinking about for the last 5 years, not full time, but a lot, and longer than that without actually working on it. So we're not going to go back in time, but I'll discuss now kind of studies we're doing in real time and what we're planning to do in the future, combining kind of priors, reproducibility, and betting. Okay, so there are lots of false results published in the scientific literature. And here are 3 famous examples. So there are, of course, psychopaths around that fake data and do crazy stuff. It's hard to kind of completely get rid of them. Fortunately, I don't think there are that many of them. But here we see the outcomes from 3 such kind of groups. Or here's the famous Wakefield et al. Paper, the one that said that vaccination against measles and other things causes autism. Turned out that it was fake. So the paper has been retracted. Unfortunately, everyone hasn't updated their beliefs, so this paper continues to have too big of an impact on the world, even though it's just fake. So we haven't kind of completely succeeded here with reputation management of these papers. There's another paper here on stem cell research that turned out to be fake. And the third example here is a famous example from psychology, so where Diederik Stapel was a Dutch psychologist who turned out to have been faking data for a long time. In papers that were published in top journals. So he probably looked like the perfect PhD advisor at some point, because if you were a PhD student and you had an idea, you would go up to him and tell him about the idea. And he said, that's great, I'll collect the data. And then the data came back, it was always, of course, perfect, and too perfect. So he was partly caught by the way the data was distributed, basically, the numbers in his data sets by Uri Simonson and others. So these are, of course, all unfortunate examples. I mean, psychopaths faking data, but maybe in psychology, this has kind of nudged psychology a bit towards becoming more worried about publishing false results. So there's something maybe positive coming out of that particular example. But there are also many other reasons why we publish false claims in scientific journals without us being psychopaths. So how many published claims are actually false? Well, it depends on, for example, the p-value. So what's the p-value? So the probability of observed or more extreme result if the null hypothesis is true. And typically we reject the null hypothesis if we have a p-value that is less than 0.05. So publication bias will also influence the share of false results in the literature. And things like statistical power. So power is something we rarely think about in economics, I would say, and in many other fields, but I think psychology takes it more seriously, medicine takes it more seriously. But in economics, we rarely think about it. Why? Because it's kind of typically a bit subjective when you do a power calculation based on some assumed effect size. So now I'm talking from my own experience, but also from how I see the rest of particular experimental economics. If you end up with a statistically significant p-value in some study that you do, so you have a p-value less than 0.05, you're typically happy thinking that, if anything, you've detected a lower bound on a true effect size. So this doesn't need to be the case whatsoever, of course. So a p-value that is statistically significant can be particularly misleading if you have a small and noisy sample. So when you do a power calculation, you do it on some assumed effect size. It could be empirical. You base it on previously published papers. So what's the potential problem here? That previous papers might report inflated effect sizes. In a sense, it could be that they're unlucky. There's some winner's curse. So if they get to actually find something statistically significant, it has to be larger than the true effect. And you can also do power calculations based on some goal. So you want to be able to find some minimum effect size. But this type of analysis can have problems. And when you get the p-value less than 0.05 in a small noisy sample, this can be very misleading because you can have what Gellman and Carlin call the type M error, so magnitude error, so you'll find something that is way bigger than the true effect, or a type S error, so that the sign that you observe, the true effect, is actually of the opposite sign of what you observe. So here's an example from Gellman and Carlin's paper on how problematic this can be. So they talk about a study on the menstrual cycle and vote preferences. So they talk about this study that compares women across the cycle, so it's a between-subject design, and they find a difference in 17 percentage points in vote preferences in a 2012 pre-election study. So 17 percentage points, that's huge for kind of a political science study. And it's a statistically significant p-value, so the p-value is less than 0.05. So problem here is that vote swings are small. People are not that flexible in kind of vote preferences, that they shift from one day liking Obama, next day Romney. So to get this 17 percentage point swing or change is just like tremendously big. So they look at the general literature on vote swings and find that an effect size of 2 percentage points, that would be the upper end of plausible differences in vote preferences. So if this is the effect size that is close to the true effect size, then the original study here looking at menstrual cycle and vote preferences actually only has a power of 0.06, so of 6% power to find such an effect size. With this type of statistical power, the type S error probability is 25%, meaning that there's a 25% probability that the true effect is actually in the opposite direction of what they found. And the type M error factor here is 9.7. So if the true effect is actually in this direction that they find, it's very exaggerated, almost by a factor of 10. So here I'll show you their graphs here. So we have the type S error rate on the y-axis, statistical power on the x-axis, exaggeration ratio here on the y-axis, and power on the x-axis. So when you have high power, you don't have any problems. The exaggeration ratio is close to 1, and type S error rate is very low. But when the less power we have, and especially over here, when power is less than 0.5, the exaggeration ratio would increase. When power is less than 0.1 here, the type S error rate increases dramatically. The question then is, where are we in our studies? And I'm a bit worried that I've been around here in some. And I haven't kind of actively tried to do anything bad yet. I'm worried that this is where I've been in a few studies. Okay, so given this problem that we just saw, we have reasons to believe that we publish false claims in the literature. Okay, but there are also lots of other problems that could lead us to publish false results. So there are lots of researcher degrees of freedom that make us have clear hypotheses, test them, and still end up with false results. So I guess this first researcher degree of freedom, fishing, here we're not really testing an hypothesis. We have some data set. We test a bunch of correlations, and we end up with something statistically significant. And this is what we end up reporting. So we all know this is not something we should do. Do we see papers here and then where we think that there's been some fishing expedition? Yes, we do. So that's probably one reason why we see false results being published. Just by chance, something will be significant, and that ends up in a paper. But then we come to the kind of more, I think, problematic degrees of freedom, where I know that I have been guilty of these practices in the past, and I'm not anymore. After kind of really thinking about this, it becomes just by having names on these phenomena, I think it makes it harder to continue with this line of research. So this histogram is supposed to illustrate p-hacking. So what's p-hacking? So you could have a very clear hypothesis that you want to test. I want to see, does testosterone cause higher risk-taking? So I administer testosterone or placebo to a group of men. So it's a very clean design, clear to test. My hypothesis is that testosterone will increase risk-taking. Then once I have the data, how exactly am I going to test this? Should I do a t-test or a rank sum test? The p-value might look nicer with one or the other. If I do a regression, should I include everyone, no matter their testosterone level originally? Do I want to control for baseline testosterone levels in both samples or not? Depending on what I choose here, I can get it. Maybe I can shift the p-value a little bit so that it just drops below the magical cutoff of 0.05. And I'm testing this kind of clear hypothesis. I'm not necessarily even thinking that I'm doing something wrong when I do this p-hacking. It's just a very natural thing to do. But then you end up with such histograms where you can look at some literature and see that, okay, between 0.05 and 0.10, you might have kind of a uniform distribution of p-values reported. And then something magical happens around 0.05. Because that's what decides whether you have a result or not. And this has been shown for a bunch of different fields that you can get this distribution. So the most interesting degree of freedom, I think, is this thing called the Garden of Forking Paths by Gell-Mann and Loken. So you'll hear Andrew Gell-Mann's name quite a lot today because I think he's a clear inspiration for lots of this research. So with this Garden of Forking Paths, you can also have a very clear hypothesis that you want to test. But if you haven't specified exactly the test you will do, there are just so many different paths you can go down, even though you're testing this clear hypothesis. So let's come back to the example where I'm giving testosterone or placebo to men. So I have this clear hypothesis and I'm testing. Then I'm looking at the data, and I see that, well, if I exclude the outliers, those that had very high testosterone levels in the beginning, so in the baseline, well, the p-values look a little bit greater, a little bit nicer, so I walk down this path, and then I might do something else with the analysis and continue walking down some specific path. But if everything would have looked good with the outliers, I would have included them and started looking at something else. Maybe I'll include age as a covariate or something. So the differences between p-hacking and forking are not completely clear. So the verb here for the Garden of Forking Path problem is forking, to fork. So forking is just so natural. But the problem is when you do this data contingent analysis, where you let the data speak, is that you end up with a p-value that basically becomes meaningless in the sense that you cannot interpret it the way we're used to. So forking, I'm guilty of forking in many papers. Until I kind of had the verb fork here, I didn't know that I was doing something problematic. So this is just so natural to do. Like, you have the intention to look at the data and learn and do the best analysis you can. But most of the time, I think we've ended up forking. And then p-values, as I said, are pretty meaningless. Okay, so we'll go through a few more examples like this, and then I'll come to our actual studies on this. So for p-hacking, there are many ways to get a p-value less than 0.05. You could stop collecting data once you have a p-value less than 0.05. You can analyze many measures, but only report those that have a p-value less than 0.05. You can collect and analyze many conditions, but only report those with p-value less than 0.05. You can use covariates, so controls in the analysis, and you get the p-value less than 0.05. And you can exclude participants to get the p-value less than 0.05. And you can transform the data somehow to get the p-value less than 0.05. There's just many degrees of freedom here. So for forking, say that I want to do a study to understand altruism from a dictator game. Sounds like the typical study I would do. The recipient can be an in-group member or an out-group member. And the hypothesis here is that political preferences matter. Not a very specific hypothesis, but there's some. I can make it more specific and still run into the same problems. So there's so many forks here. The effect could be there for left-wing voters and not for right-wing voters, or for right-wing voters and not left-wing voters. Could be there for men and not women, or women and not men, or both genders. Maybe it interacts with age. How would you define left and right? Strong versus modest? Should you include everyone in the data or throw the middle guys out? Or are they the interesting ones? How do you define altruism? How much you give in a dictator game, or whether you gave or not? What tests are you doing, parametric or non-parametric? You see, there are just so many potential forks to go down, even though I had a somewhat kind of clear thing that I'm testing in the study. And it's enough that you only do one test and you're actually forking, because if you would have found something else in this first test, you would have continued down another path. So you're basically always forking, I think, if you don't say exactly the test that you would do ahead of time. Okay, so priors are also relevant for the number of, or for the share of false results being published in the literature. So what's a prior here? It's the probability that the hypothesis is true. So this is typically subjective and inaccessible. How do I get your priors about water having memory or whatever we're thinking about? So I think we have a kind of solution when we look at prediction markets. So that takes me to the importance of replications. I mean, replications are kind of key in the scientific process, and we know this. Kind of the question I want to ask at the end of the day is like, are we rewarding replications enough given their importance for our understanding of scientific phenomena? So I think replications are great to assess the reproducibility of some specific field, but I think they're also great as threats. So if the threat of replications kind of loom over all of us, maybe we do better studies, fork less and do higher powered studies in the first place. So what have we been doing on this in this field? So I've been part of the reproducibility project in psychology. So this is a big collaboration of 270 researchers across the world, where we did a large-scale open science collaboration to estimate the reproducibility of psychological research. So we look at 3 different journals in social and cognitive psychology. We ended up taking 100 of these studies and replicate them with high-powered replication. I think average statistical power in replications were 90% to find 100% of the original effect size. So if you think that kind of the original studies have inflated effect sizes, 90% power is maybe not that high, and maybe we'll actually get some false negatives then. But that's what we ended up doing in this project. So we have 270 authors on this paper. So there were 3 goals with this project. One, to assess the overall rate of reproducibility of psychological science from these 3 journals. So reproducibility here was defined as a replication. The replication effect would be in the same direction as the original study and have a p-value less than 0.05. The second goal was to identify obstacles in conducting replications. I think some anthropologists should have followed this closely. It was some interesting things happening in this project. And the third goal was to identify predictors of replication success. Is there something in the original papers or something else that we can use to predict replicable results? So this paper was published in 2015 in Science by the Open Science Collaboration, so these 270 authors, including a few Swedish ones. So here are the left figure here. We have the p-value on the y-axis, we have original studies, and we have replications. So among the 100 original studies, 97 reported statistically significant results, so p-values less than 0.05. So the p-values are, of course, all but 3 distributed below 0.05. You barely can see anything here because they're also close between 0 and 0.05, whereas the replication p-values are, as you can see, a lot more dispersed. If we look at the effect sizes are kind of fairly large and positive here in the original studies, and are more kind of dispersed and closer to 0 in the replication studies. So in total of these 100 studies, 36 replicated. So about a third replicated. So this was then with our criteria that the effect had to be in the same direction as the original study and a p-value less than 0.05. And as I said, kind of maybe we're giving some of these papers a hard deal in the sense that they were probably victim of a type M error. So they had inflated effect sizes in the original studies. So if we and other people who have looked at this data later say like, okay, 1/3 of the results clearly could not be replicated. 1/3 of the studies clearly were replicated. And for about a third of the studies, we don't really know. We should do them again, maybe with even higher power or something. I can skip this. So there were a few predictors of replication success. So original p-value was one predictor. The lower the original p-value was, the more likely it was to replicate. I mean, you can p-hack yourself to something less than 0.05 maybe, but it's hard to p-hack yourself maybe very much lower than that. The original effect size, so the larger it was in the original study, the more likely it was to replicate. There was some suggestive evidence of social psychology being less likely to replicate than cognitive psychology, but now we're not talking large sample sizes, so it's just indications. Also, some evidence suggesting that interaction effects were less likely to replicate than simple effects. So in particular, these triple interactions were the least likely to replicate. Kind of surprising effects, as coded by the replicator team, were also less likely to replicate. So we did something similar, but the light version, basically, for papers in experimental economics. So we went through 2 of our top journals, American Economic Review and Quarterly Journal of Economics, and looked for all between subject design experiments in the lab. They were basically testing some hypotheses. So there weren't that many. So we ended up with 18 such studies between the years 2011 and 2014. We only look at main effects here, no interactions. So when we're going to compare it to the psychology results, kind of we're setting it up so that economics will almost perform better than psychology. So that's good to have in mind later. We have 90% power here to detect the original effect size with a p-value less than 0.05. So the same replication criteria as earlier, and we have a prediction market and a survey. So I haven't mentioned prediction markets yet, so we'll come back to that in a little while. So we published the outcome of this replication project in Science last year. So here we have the 18 experimental economic studies. We have 0 here being no effect. We have 1 being the same effect as in the original study. And then we have the replication outcomes with their 95% confidence intervals. So here we find that 11 out of 18 studies replicate, so approximately 60%. So it looks like a little bit better than in psychology, but again, we can't really compare them. 18 is also a ridiculously small sample, and we have different inclusion criteria. But kind of with power here, we should have expected 90% to replicate, and we don't. Here we're also including the meta-analysis. So when we combine the original data with the replication data, where do we then end up? So there were some kind of borderline cases over here, like Ericsson and Fuster, where the p-value was just above 0.05. I think they were a bit unlucky. So combining it, the original data with the replication data is a statistically significant value, but then on the other hand, the replication data is the only thing that shouldn't be biased, whereas the original data of all studies, if you don't have a pre-analysis plan, is probably biased, basically, I would argue. Okay, so where do prediction markets enter here? So more than, I don't know, it must have been about 10 years ago, I read this paper by Robin Hanson called Could Gambling Save Science? So Robin Hanson here is basically arguing for the use of prediction markets in science in order to aggregate information and also set up incentives for discoveries in science. So I read about this. Thomas Pfeiffer, who's a computational biologist that I work with, he read about this. He was interested in quantitative biology, so he was studying how people were citing yeast genes. I know nothing about yeast genes, but there are tons of citations for these genes, and he would look at patterns of citations, etc., and discoveries. And my husband, who's also an economist, the three of us read this paper and talked a lot about this and said, like, wow, there are all these kind of cute experiments around. Do we really believe in them? Not necessarily. It would be fun to set up a prediction market and have people bet on the outcome of these replications if one were to actually do replications. And then we didn't think about this for 5 years. And then came the reproducibility project in psychology along and kind of made our dreams come true. That's when we could take prediction markets to science. So what do I mean here? So prediction markets are basically these platforms where you can trade basically on future events, on whether some future event will happen or not. So in a very simple version of the market, you trade on, say, a political event. So here, would Obama be elected as president in 2008 or not? So the contract here is worth $1 if he wins and $0 if he does not win. So the question is, for which price are you willing to buy this contract? With some caveats, you can basically interpret the price of such a contract as the probability that the market assigns to this event happening. So if the price is 91.5 for this contract that is worth 100 if Obama wins and 0 if he loses, we can interpret this as the market thinking that Obama has a 91.5% probability of becoming president. So if you think that this is way too high, well, you should go short on this contract. And if you think that no, it's like a 99% probability that Obama wins, well, you should buy this contract. You should go long in it. And depending on your behavior and the behavior of others, this will, of course, move the price. So previously, in kind of with previous elections and other events, prediction markets have typically performed better than polls in predicting outcomes. So now with Brexit and then Trump, prediction markets were not that good, and neither were polls. And they seem to have been feeding each other with incorrect information, basically. So prediction markets can work well. Obviously, they don't work well all the time. Do they work well in science? Well, we'll see in a few slides what we've found so far. But this is kind of the setup of a prediction market. You bet on the outcome of some future event occurring or not. Question is, what probability do you assign this future event? So what can prediction markets be good for? Well, for information dissemination. Prediction based on the trader beliefs is communicated to the public. That can be interesting in itself. In the same way as we are interested in maybe political polls, etc. Can be great for information aggregation. So information dispersed among traders is combined, and the market prediction is equivalent to the prediction of a single trader that possesses all of this information. And there are lots of old and new experiments by experimentalists like Charlie Plott and others on prediction markets, kind of saying how they perform well and typically perform well. Okay, so what could they be useful for more? Well, you can have incentives for discovery. So traders with an information advantage can benefit from a market. So if you set up some type of scientific market, well, you can give them incentives to invest into finding out what the truth is here. And you can have a market maker who subsidizes discovery. So always offers buys and sells, for example, and will adjust prices after a trade. Like Hansen's logarithmic market maker, which is what we use, and I'll come back to that soon. So it's kind of clear how prediction markets can be useful in science. Well, to disseminate what people think about some specific phenomena, let's say climate change, what would the price be on the probability that we basically assign the probability that we assign for some temperature change over some defined time period. If we have such a market, we can kind of easily disseminate a general opinion about things. Great for the aggregation of information, and maybe also to set up incentives for fund research. this is a part that I've been the least interested in so far. So what have we done? So we've done prediction markets on 44 of the 100 psychology studies. We did 2 sets of studies, one in 2012 and one in 2015. The market was open for 2 weeks at each occasion. We had about 45 participants at each time, and they were endowed with $100 each to trade with during this 2-week period. In experimental economics, we ran a market on the 18 studies I described earlier. We had the market open once then for 10 days, and we had about 100 participants. They were given $50 each to trade with. So in these prediction markets, we had one central hypothesis for each replication study. That's the hypothesis that was to be replicated, so it was kind of clearly defined. We had binary outcomes for this hypothesis. Will it be replicated or not? Where replicated means that it had an effect in the same direction as in the original study, and a p-value less than 0.05. Participants traded contracts that paid $1 if the study replicated and $0 otherwise. So the price here can basically be interpreted as the predicted probability of the outcome occurring. So the predicted probability that the hypothesis is kind of replicated, with some caveats by Charles Mansky and others. And we use the logarithmic scoring rule here, where we basically, if you are a trader here, you do not need to find a counterparty who's willing to sell to you if you want to buy. We are your trader. We are your counterparty all the time. So we do a market, and I'll show you more details about the market. But we also do pre-market surveys, where we basically try to elicit people's beliefs about these hypotheses. So we ask them, how likely do you think it is that this hypothesis will be replicated? And how well do you know this topic? So this is what the prediction market looked like for psychology. So basically it looks a little bit like you're trading stocks or something. I mean, it's like a trading interface where you have a list with all the hypotheses that you can bet on, 20-something for each psychology market. You see the hypothesis number, the name of the authors, the name of the paper, the score here, which is the price. All prices are out at 50, and then they can potentially go up to 100 or down to 0. This price has just increased by a little bit, so someone kind of went long in this, thought that the probability that it replicates is higher than 50%, so they're willing to buy it. I can click on this, and then I can choose to go long in it or go short in it. I can choose how much money to invest here. And then I have my answer page here, where I have all the hypotheses I've been betting on and what's been happening to these hypotheses. So what did we find in psychology? So for these 44 studies, one was actually canceled in the sense that they changed the hypothesis, and one will never be performed. But for the ones that we do have, so we have the market price here on the y-axis. So it can go between 0 and 100, and it's pretty dispersed, as you see, between something like 17 to 90-something. And we have the hypothesis here, ordered by market price on the x-axis. So we have failed replications in red and successful replications in black. So the squares here are the market values for these hypotheses or these replications. The filled dots are the survey answers, and the unfilled ones are the expertise-weighted survey answers. So we basically see that there's a lot of agreement between the survey and the market. But in the few cases where there is disagreement, the market predicts it correctly and the survey fails. So here, with this type of dispersion, we basically said that if the market price is above 50, the market believes that the study will be replicated. And if it's below 50, the market does not believe that it will be replicated. We can do this kind of less binary too, but this is one simple way to look at it. So the market is significantly better than chance in predicting the replication outcomes, whereas the survey is not. So that's evidence that there is something to it. The market doesn't predict it perfectly, But there's something to it, and what could it be? Well, the market allows you to be Bayesian in the sense that you see what other people are betting and you can kind of update your beliefs. And if I have a hunch that this study might replicate and then I see that everyone else really believes in it, maybe it makes me more likely to believe in it. And if there's some study I'm skeptical about, there could also be this reinforcing effect. But we also have incentives in the market, and we don't in the survey. So that's also something that differs between these setups. So in psychology, it looked pretty good. I mean, we wrote this paper, published in 2015, where we were very excited. And here we're a bunch of people. So I'm an economist, we have a computational biologist, economist, software developer, computer scientist, psychologist, and economist. So we're kind of interdisciplinary team here. And this is, now I remember to point out some people, at least. Typically I forget. Okay, so we did the same thing in economics. So we had a prediction market that looks slightly different because we developed it ourselves at that time. We give people price history, unlike in the previous psychology markets. But the outcomes in terms of the market performing well is not at all as clear. So for economics, all prices and beliefs are actually above 50%. So people were kind of more optimistic about the economic studies. And actually, they were correctly more optimistic because there was a higher replication rate for the economic studies. So the average prediction here is 75%, and the survey average is 71%. So neither of these are significantly different from the 61% that we actually observed. So the survey and the market were optimistic here.
So the players knew quite a lot, maybe you should say. They were quite
so these were
experts.
So in the psychology market, we largely had psychologists betting. So when we proposed this prediction market to this big network of psychologists, I was afraid that someone would say, like, what are these crazy economists doing? But everyone was just very enthusiastic. So then when we proposed this to the big Economic Science Association email list, basically invited all experimental economists who wanted to participate. And yeah, I guess they weren't skeptical. Maybe they were less excited because this is kind of normal for them, maybe. But they were all kind of mainly economists betting here in the economics market. So there's some selection, different selection in bettors and traders. Okay, so looking at the replications in economics, there are a few things that do predict whether a study was replicated in economics. So, for example, the original p-value correlated negatively with the replication being successful. So the lower the p-value, the more likely it was to replicate. Same thing with the effect size. The lower the p-value, the higher the effect size. So the lower the original p-value, the higher the relative effect size. So survey beliefs and prediction market beliefs were also correlating with the original p-values. And the original sample size correlations were also positive to the replicated p-value and a bunch of different things. Basically, there were things in the replication, in the original paper, that were useful in terms of predicting replication outcomes.
So these were just binary correlations, right?
Yes. Yeah. So comparing psychology and economics, as I said, is not really comparable because we have different inclusion criteria. We have a smaller sample. We have 18 studies. In psychology, they had 100 studies. So it's just like the psychology paper is really the biggest thing here. But looking at these 6 replicability indicators, so whether it replicated, relative effect size, survey beliefs, prediction market beliefs, etc. Okay, we find a statistically significant difference here between economics and psychology in terms of whether it replicated. And this basically spills over to the difference in survey beliefs and prediction market beliefs. So I showed you earlier that in economics, people were optimistic in terms of replicability in the market and in the survey. People were also a bit optimistic in psychology. So given this difference here, these differences over here for survey beliefs and prediction market beliefs also make sense. Okay, so what we do with these prediction market prices, though, is so with these we can back out something that John Ioannidis first called the positive predicted value, so the PPV. So the prediction markets can be used to estimate the probability for each hypothesis to be true, and this is what we call the PPV. So the price in the market, PM, reflects the probability that a published result will be replicated, not the PPV. So the market participants here knew the statistical power and the significance levels for each study. So the power was always less than 100%, and we had the 0.05 p-value cutoff. So if we combine the prediction market price, PM, power, and statistical significance, this allows us to estimate the PPV, or the probability for an hypothesis to be true. So basically, we have this market price. With power and p-values, we can back out this P1 here. So this is a probability that the hypothesis is true once we have the original study, but before we have the replication outcome. So given that we have this P1, we can back out this P0 here, which is the probability that the hypothesis is true before it's even reported in the initial study. And once we have, so with P1, and once we have the replication outcome, we can also get this P2, which is the probability that the hypothesis is true once we've had the initial study plus the replication study. So we do this little exercise, and we take it with some grain of salt, because we have kind of phishing and p-hacking and other things going on, kind of not for all of the initial studies, but probably for some subset of them. But if we do this exercise, and maybe we shouldn't focus too much on a specific number, but more like the ballpark, we find that this P0, so the probability that the hypothesis is true before the initial study, the median P0 here is pretty low. So the median is around 10%. So this is one way to say that lots of surprising hypotheses are being tested, where surprising also means low probability of being true. So then we have the original studies reported, which all find statistically significant effects. So then this PPV, the probability that the hypothesis is true, moves from a median of 0.10 to a median of 0.55, 56. So once we go from no study to one study, we don't move up to like some 95% probability that the hypothesis is true, the way we sometimes interpret p-values. So we're around 55% here. Then once we have a successful high-powered replication, this probability moves up to close to 1, median probability close to 1, for the successful replications, and it drops even lower for the unsuccessful ones. So I think this is a figure showing the importance of replications. Basically that we can kind of shift the probability up or down quite a lot here. Okay, so what have we learned from this exercise? So a common interpretation of the p-value, as I said, of a p-value less than 0.05 is that you have a 95% probability of the hypothesis being true. So for this to actually be the case, this p less than 0.05 finding needs to be replicated in a high-powered replication. So given kind of the importance of replications here, do we have enough incentives for replication? And I think the answer is no, even though it's kind of being rewarded more now than before. I think kind of I'm still pushing for the importance of replications. And if there are kind of, given this, and given that there is some kind of wisdom of crowds, or the survey performs pretty well and the market performs pretty well, why are so many false results being published? Kind of in economics and in psychology and in other fields. So we're continuing with this in various other ways right now. So the experimental economics team, we teamed up with Brian Nosek and his team. So Brian Nosek was basically the psychologist who led the whole reproducibility project in psychology. So fantastic person. And so we teamed up, and we now do a big replication project of papers in social science published in Nature and Science. So we've gone through all social science studies from Nature and Science from 2010 to 2015. We do not only do lab studies with students, but there are some studies that we just cannot replicate for various reasons in terms of getting similar samples, etc. Like for us to get 500 bankers, it's not that easy, so we had to kind of exclude that study. But there are lots of other studies that we can replicate, so we do these. We have high statistical power, way higher than before. So we've talked already about this type M error, the magnitude error. So very likely that the results in the original papers are inflated. The effect size is way bigger. The reported effect size is a lot bigger than the true effect size. So here we go for 90% power to find 75% of the original effect size. If we then do not find support for the original study, we do another round of replication to have 90% power to find 50% of the original effect size. So this basically makes us get a 4 times larger sample size than what we would have if we did the old version of power with 100% effect size. And the false positive rate only increases marginally from doing this. So we want to rule out false negatives, basically. So the replications are taking place. We've done more than half of these already. We've done prediction markets and survey already performed. So in a year, we'll have the results from this experiment. So again, I'm extremely excited, of course, but the sample size is 21 again. So it's not a big, I don't think one study here is really what counts. It's like we have to do many of these big projects in order to end up with something big at the end of the day, and then we can look at all of it and say, what does it look like? So not just put emphasis on one study. So another thing we're thinking about is looking at decision markets. So here, instead of just having a prediction market, we can let the market actually decide where we go next. So if I have you bet on the outcome of a bunch of different hypotheses, I can, depending on how you've been betting, I can choose to run some specific replication. Maybe I want to do studies where there's the most disagreement between people in terms of what they think would be replicated. Or where is there just the highest degree of uncertainty in the outcome, or the highest chances of observing an effect. And we can decide this ahead of time and then let the market choose what we're going to do, basically. We're also doing more work where we compare prediction market to incentivized surveys or surveys with feedback and other things, which other people are also exploring, but in different contexts, basically. So this is not just a experimental economics or psychology phenomena, this irreproducibility business. So people have been talking about this for a long time in other fields. So here's a kind of shocking picture from medicine, so from preclinical research. So these are papers, these are individual data sets that were reported in other journals, like this Amgen study was published in Nature, etc. So here they go through a bunch of these big irreproducibility projects or reproducibility projects in medicine. So here we have irreproducibility on the y-axis. So not reproducibility, but irreproducibility. So here we have 53 studies from Amgen. So these are kind of cancer biology papers. So important outcomes, stakes are high in many ways. So what's the irreproducibility here? Close to 90%. So we look at these other sets of studies, and irreproducibility is just very high. So this is kind of not just a social science problem, it's a general problem, and I mean, stakes are a bit higher here than if a paper is published in psychological science or AR.
By the pharmaceuticals?
Yeah, so I mean, maybe I'm naive, but I would think that they want to get it correct in the sense that they want to do medicines on this, but I'm maybe naive. But it's, I think it's like a very sad slide. So why are what's happening here? So okay, we've already discussed these phenomena, about power, forking, p-hacking, all of this. I think all of these are important contributors to kind of the body of false results. I don't think it's psychopaths or unethical researchers doing bad research. I think it's ethical people trying to test interesting hypotheses, and then somehow we end up forking. I've forked in the past, and I'm sure many other people have forked and are forking, and we just don't realize this is a big problem. So another interesting phenomenon, so we've talked about this earlier today, is this what, again, Andrew Gelman calls a time reversal heuristic. So let's say we have two studies. We have one study with 200 people, men and women, exploring whether power posing affects risk-taking and hormones. So 200 people, they're randomized to a high power pose, like this, or a low power pose, like this. for a minute or two for each pose. So the experimenter here is blind to the condition, so does not know whether a person is put into a specific pose and then gets to do a risk measure to look at risk preferences. And the hormone levels are measured, testosterone and cortisol. And they're also asked about how powerful they feel. So this study of 200 participants come out and finds no effect on high power poses on risk-taking, testosterone, or cortisol. Some effects on the feelings of power, but lots of tests have already been run on men and women separately too, etc. So lots of no results. And then you have a paper with 42 people looking at power posing, and it's not experimenter blind. So again, high power or low power, and they find dramatic effects on testosterone, increased testosterone, lower cortisol, increased risk-taking, increased feelings of power. Okay? So first we had this big 200 people study finding basically nothing, and then we have this replication with 42 people. Which do you kind of believe in? How much does your prior shift from seeing this 42 people study? Maybe not that much, given that you just saw nothing in 200 people. But if the results would have been the opposite, everything is just different. So this is what we've experienced. So power posing actually happened in the other way around. The first study had 42 people, showed these dramatic effects, and then we come with a replication study, basically finding nothing, with your soon-to-be colleague Eva Ranhill. And basically, lots of people still put all the emphasis on this first study of power posing. But there's been so much discussion about this, so that the first author of this paper, Dana Carney, has now written an open letter saying basically, I don't believe in power posing. We p-hacked, we had the weird exclusion criteria, and we didn't realize at the time that we did something wrong, but I don't believe in power posing. I don't think you should either. I wouldn't encourage people to do research on power posing. Like, wow, I think it's just fantastic that she goes out and says this publicly, like, and doesn't just defend her study forever. I mean, we can all run into false positives. Doesn't mean that we're bad guys. Like, things happen. We do mistakes. Doesn't mean we're unethical or Macchiarini. And I think it should be a bit forgiving too. Ultimately, I think we're after some truth, right? Or I hope we are, at least. So disbelief is an option. So why am I saying disbelief? Well, some of you have read Kahneman's book, and he talks about a bunch of these studies, priming studies, where if I read words related to Florida, etc., I move slower in a room. If I hold a warm cup, I become more altruistic than if I hold a cold glass. So these are results that you see in these low-powered studies. Then once you replicate them, they typically don't survive unless you interact them somehow, the outcome variable, with something else. Some variables, like, they can just never survive on their own. There has to be some context all the time, kind of making you end up seeing them. So the weather outside matters for whether the Florida effects exist or not. They're only young people, or only old, or something. Like, you always have some excuse why the effect does not survive. And I think that's just very problematic. And these are not Kahneman studies, by the way. He has now basically written a letter saying that he doesn't, he also fell for the law of small numbers when he was writing about these studies in his book. But disbelief is an option. If we see some spectacular result in just one study with a small sample size, let's wait for the replication until we kind of put too much emphasis in it. I mean, the TED Talk based on this 42-person study has 35 million views. How many views do you think my talk will have? So, yeah, it's a tough job, but it's okay. Okay, so and now maybe a final quote from Andrew Genman of today. So, I mean, he talks about all of these studies and kind of our flexibility with theory. So if we have this theory that something will affect something, power posing will affect risk-taking or hormones or whatever, and you happen to find some statistical error in my paper, that's okay. As long as kind of somewhere in the paper there's a p-value less than 0.05, then that's support of my theory. So there are so many examples of this, not just for power posing, but for phenomena in economics, psychology, other fields, you name it. So all that matters basically is that there's something somewhere that has a p-value less than 0.05 in the study, and you're all set. That's support for your theory. So I think we have two flexible theories in many ways, and yet we don't want to narrow it down. But this is something we should kind of consider we who kind of wouldn't want to do experimental research inspired by theory sometimes. So again, this takes me to the importance of replications. We need replications in order to kind of understand more about the world. And then again, the question is, do we have enough incentives for replications? So I'm glad that these papers are now being published. So our power posing replication was published in Psychological Science. If this was 5 years ago, I don't think that would have happened. But there's something going on. So I think this kind of replication crisis that in the social sciences started in psychology has been so beneficial for the social sciences. And I think that psychology is now ahead of economics in kind of really incorporating what we've learned into psychological research. Right? That's fantastic. And economics, we're lagging a bit behind, but eventually we'll get there too. So besides just running high-powered replications, there are other solutions. So pre-analysis plans that we say exactly the tests we will do. And we don't want to limit ourselves too much. We can have exploratory analysis, sure. But at least kind of, I think that pre-analysis plans for me would have saved me a lot of time, energy, and resources. Because I wouldn't have been kind of chasing these false positives that were basically dead on arrival. We maybe should obsess less with p-values. So last time I mentioned Gelman, he would say, well, instead of pre-analysis plans, when you have this big registry data that you've looked at and other people have looked at, so you cannot really do a pre-analysis plan because you already know things about the data. We can do hierarchical modeling and not just obsess about p-values the way we do it. But in general, I guess, when we can, we should just have higher power, do larger sample sizes. Instead of running 5 treatments or 5 experiments, just do one high-powered one so we know exactly kind of what we're doing here. So I think that's it for what I wanted to go through. And if anyone wants to collaborate on something, you know, please contact me. It would be great. And I'm willing to update. I've probably said some things that won't hold in 5 years, and that's okay. Like, we're updating constantly. So that's fine. Thanks so much. Any questions?
So thank you so much for extremely insightful and exciting and stimulating talk. Now there is time for questions. We have, I'm sure there are strong views and pressing questions out there for Anna. So who would like to start?
So the first question is, how did you select your samples? I mean, if the study used American students and you use Swedish students, you might get different results because people are different. And another question is that, I mean, it's impossible to remove all the problems, but in time series analysis where I work, we usually look at diagnostic tests of the models. We try to estimate the model that fit the data. But did you care about that in your analysis here? My impression is that in microeconomics, they don't care. You hardly ever see any diagnostic test. You say, well, they might remove an outlier, but you remove an outlier if it affects the, if the specification test fails. And you transform the data if the model doesn't fit the data.
Okay, I'll start with the second question.
So I wonder if that, I mean, isn't that part of the solution? That people actually estimate models that fit the data?
So I would say most of the time we're not testing any models, at least for these experiments. We're basically, I mean, this is why I love experiments, because you can really get to causality. You have a control and a treatment, and you randomize people to this. There's no model to test. It's basically like, does the treatment group differ from the control group? I don't want to run into a model here. I think it's just, typically we're just interested in like...
use OLS, you have, the OLS estimation is based on some assumptions.
But okay, but I decide ahead of time basically whether I want to do a t-test or a Mann-Whitney or something. So I assume something about the distribution of the data. So we don't do the model stuff. Maybe we should, but it sounds like it would encourage us to do some forking. Maybe that's fine in some instances, but I don't see that this would solve much here. And outliers, like for the types of experiments that I'm doing, there are no outliers, I would say. But for other phenomena, I understand that, sure. But this is like, now I'm answering for experimental studies. And I think these are like experimental studies in economics and psychology. There are no outliers. Yeah, but for other types of studies, sure, but not for experiments. So the first question, like the sample. So when we do the replications, to the extent that we could, we try to actually replicate them in similar places. So for the experimental economics paper, for example, we had a handful of studies that were done in some of the Harvard labs. So we did them in the Harvard labs again. So that was typically not the case because you cannot access such, like all labs across the world. But remember also that these papers are not written in a way that, oh, we find this fantastic effect on a set of Columbia University students, and we only talk about the generalizability to Columbia students. No, we talk about this as like a general phenomena that applies to anywhere if you do this type of randomization. So I put some kind of, I think the pressure is on the original authors to kind of either tone down their claims or be willing to say like, sure, if I found something on American students, I should find it on Italian students if I have this randomization. So that's my general take on kind of external validity and generalizability.
If I can interrupt in between, someone else think for more questions. But I mean, for some kind of data, you cannot really get more data. The data is what it is. Maybe you observe something in the real world. And then, of course, you could still do replication studies in the sense that you could test different specifications and see how robust the findings are and so forth. And such studies are, of course, there. And also that probably we should do more of, I guess.
Yes.
Because Forking is of course, is still working on that data too. Even
yes, but to the extent that I worked on non-experimental data, I also kind of wish that I had a pre-analysis plan there, because then you have your observation data from Statistics Sweden. There are just so many possible regressions to do. Should I do OLS, log it, whatever? I wish I can kind of decide this ahead of time so that I don't have to decide it based on a p-value or something. Which I'm not saying that you necessarily do, but kind of it gives you some freedom, and I want to reduce degrees of freedom for research. That's probably different.
Have you read the stuff by David Hendry and others in Britain? I mean, this general specific approach where, I mean, it's not an option whether you have a log linear or not.
Maybe this depends on the field that you're in. But like for the questions that I'm asking, I think we don't have to. We can kind of tie our hands more, and that's probably not the case in other fields. I think when you kind of you're open with what you're doing, things get a lot better. And you're like in time series stuff, you are kind of very clean with what's going on. In many other fields, that's not at all clear. So you end up seeing some result, and you have no idea how many other things have been tested, and that I think is very problematic when we interpret p-values in particular.
Okay, Toby.
Thank you. Thank you for your presentation. You made many good points. But when we teach, I have one question, one criticism, I would say. When we teach psychology students experimental method, and I have done that for many years, we don't tell them necessarily that they should increase sample size, because there are other means to increase power. So you said instead of doing 5 experiments, you should do 1 experiment with 5 times so many participants. I don't agree to that in general, because I think it's value in doing many experiments with partly different or part replications, as the term is. So you can do a series of experiments with part replications. I think that's often a wiser strategy in experimental research.
So. Sure. I mean, I'm probably exaggerating a little bit when I say some things, but we don't have to kind of do 5 times the sample sizes. But if we do these many small experiments, this is basically what I'm worried about. That if we do kind of 5 very low-powered studies, what we actually end up seeing is not very informative in the sense that the probability of this type S error, that what you observe, even if it's statistically significant, is actually in the opposite direction. That's what I'm worried about in seeing many small scales.
We are not telling them to underpower. We are not telling them to underpower.
No, but sometimes we don't know the power. Or but based on some assumed effect size then. No, I've kind of run underpowered studies, but I've been doing studies on candidate genes, so that's by definition completely underpowered, and I didn't realize it at the time. But I guess within subject studies also give us higher power. I would love to.
Sure.
Are you opposed to what's called in psychology conceptual replication?
No. So I think conceptual replications are great. So it doesn't have to be direct. I mean, conceptual replications are in some ways more interesting, because if it holds in a direct replication but it's just so specific, doesn't really teach us much about the world. So eventually, I think conceptual replications are the most interesting thing. So I completely agree there. And I mean, it all kind of depends on where we are here on just on power, basically.
Yeah.
Right.
Okay, next one. What's that?
Yeah, thanks for a very interesting talk. So I was thinking about this, like if we are moving towards more, we want more field experiments. So that would be really tricky to replicate. You said yourself that you were excluding bankers, for example. So how would we, do you have any reflection on how we go about replicating?
No, I mean, that's difficult. So then I guess, I mean, I don't care about replications per se. I kind of want to get less false, like kind of more true results published. So one way there would be to have more pre-analysis plans for the field experiments too, which is happening. So for kind of randomized control trials in development economics, they have pre-analysis plans now to kind of avoid many of the problems that we've talked about. So I think that's more of a solution there, because you cannot replicate many of the most interesting studies that are being done in medicine and economics and elsewhere, because like the field aspect to it and the sample sizes, etc. So, yeah. So unfortunately, we can't replicate everything, but there are still solutions, like pre-analysis plans.
Yeah, couldn't that be a response to you, Dick, as well? Or could you do a pre-analysis plan?
If I could do a pre-analysis, I would say the strategy would be to put in all relevant variables. You know, all the relevant ones you put in, and then you make sure you have a statistically well-specified model. Yeah. A statistically well-specified model, and then you kick out things that are insignificant. That's the strategy. And during this process, you make sure that the residuals are okay, normally distributed. And then, of course, you have outliers. Then you have to motivate, you know, what you do with them. You have to have a good explanation. Because usually an outlier, because it's not captured by the explanatory variables, you can't explain them. But that's part of the analysis.
Okay. I don't know if you want to respond. Otherwise, in more general, in terms of forking, don't you think you could solve part of the problem, maybe even a large part, by if the journals always consistently forced each author to publish all data online and also the codes online, both raw data, sort of modified data, and all the codes, because then you would, of course, if they were easily accessible for everybody else, then you could see if most of the specification did in fact not lead to p-values less than 0.05 and so forth.
So I think posting data publicly available is great in one way. But I mean, so in some of the kind of the forking exercises, they don't claim that the results are more general. They say, oh, we find it in this specific subgroup, which could be very interesting.
Yeah,
so
sure.
Like heterogeneous effects are, of course, amazingly interesting. So I don't think they claim more than that. So if you look at the data, yeah, you see exactly what they reported. They only find this in this subgroup.
Yeah, but
like
quite often you get an interpretation that this is much more general than it is, but while in fact it's only valid for very specific circumstances.
But I think in general, like if
Maybe.
the data
Okay.
becomes available, it's
Gunnar?
Thank you. Is it on? Yes. So I would like you to elaborate a little bit on the incentives of replicability or replication. So I guess that there are a lot of examples of lack of incentives for it, but what is it really that you're looking for? Is it on the publication side? Is it on the funding side? What have you seen in the past, and what would you like to see in the future?
okay. So yeah, higher incentives everywhere. No, on the journal side, on the funding side, everything. No, I'm exaggerating, of course. No, but not that much exaggerating. But so I think so there's some like history in economics, for example, where journals they publish something, some positive result on fairly small sample or something, and then other people cannot replicate on larger samples, and the journal think they have no responsibility. Like, why should they have to publish this? It's not interesting. But it can. First of all, it is interesting, and I also think that they have some responsibility. So there's something wrong, there's something weird when they don't feel like it matters for them. I cannot even kind of understand how they reason here. So I can't even say what I think they're doing. But then for something like psychological science, they published a power posting paper a few years ago, and then our replication comes, and they published that too. It's a very short paper, and we have tons of stuff in the online supplementary material, but the message comes across. Okay, we have a high-powered replication, we cannot replicate it, and they feel like they want to clean up some of the false positives. And this is not saying that the original people did anything bad or the journal did anything bad. False positives happen by chance and not only by forking. So I think if we're out to get some truth, we just have to reward replications. And then, yeah, sure, funding them, etc. So now I guess we realize that if we do these large-scale collaborations for replications, so 100 replications, then it's not going to be ignored. But I guess if you talk to your colleagues or friends, when I do it, everyone has basically some replication, failed replication in their luggage that they haven't reported anywhere, because maybe they tried to publish it or didn't even try because no one cares. And people should care if it's high-powered. I mean, a low-powered replication is not that meaningful. In the sense that
if it's equally powered as the first one and the opposite result, of course, it's an indication.
Yeah, but there are some examples where some replication gets a lot of attention and the power is so amazingly low.
Yeah, of course.
Then it's hard to.
Yeah. Okay, more questions? Some are close to raising their hands, but still not. Okay, one more chance. Yeah.
I'm really thinking about.
Wait, we get the phone. Thank you.
I'm really thinking about your betting side from a business point of view, but I have some difficulties thinking who would be. How large would the group of people who would be betting be? It would be difficult to set up the company, I think.
Yeah. Oh, so there are companies. So the biggest one up until recently was Intrade, this American prediction market company that was shut down for accounting reasons, and and it was of course also not legal in the U.S. because it was considered gambling. But everyone I knew in the US had an account there, so it was. But anyway, so I feel like there's a spot to fill in terms of becoming the new Intrade. So there are all these studies, as I said, on comparing political polls to prediction markets, and then when the prediction markets perform better, the sample sizes can be a lot smaller than for a poll. Like if you have a poll of 1,000 people and you ask them who would you vote for, okay, you get one observation per individual. When you have people bet in a market and you ask them who will win the next election, I'm not really betting according to my political preferences. I'm betting according to my beliefs about the world, right? What do I read about in the news? What do my friends and family say, etc. So in that sense, you're aggregating more information than just one individual. So there are tons of studies by, for example, my co-author Yiling Chen. She's a computer science professor at Harvard. She's done mainly theory, but also some empirical stuff on prediction markets, where they basically see, yes, how many participants do you need in order for the market to not be too thin, etc. So look into her work and Robin Hansen's work on prediction markets. So I'm no prediction market expert, and I'm not trying to be either, because I can talk to the prediction market experts. So some division of labor is great. So, but I think prediction markets are interesting. Are they the solution in order to gather, aggregate information? I don't know. Maybe surveys would be better. That would be easier for me, actually, because then we can just survey people instead of running markets, which is more cumbersome, but it's also fun, of course.
Okay. Dick has another question.
I have another question. What's the relationship with the t-value and the probability that you could replicate? So if the t-value was 4, was much more.
So we haven't looked at that. We can.
Well, the p-value.
Yeah, sure.
So
the lower the p-value, the more likely it was to replicate. More than that, I don't know. No, I can't remember.
Okay, because it's interesting if you would change to a 1% significant p-value of 1% instead of 5%, would it be very much more likely that?
I think that's
or down to 0.
Okay, so just trying to remember a little bit of what we looked at, I think that would make a difference. Because you can p-hack yourself some way down, but not. It's harder to get to 0.01.
If you combine all the studies and just look at the graph of the p-values and the probability.
Yeah.
Okay, Tommy.
Would you mind a question from a business administration?
Great.
a lot of my colleagues are doing what they call qualitative research. I wonder if you have any reflections about that and reproducibility.
So, yes, this is a very interesting question that I don't have a good answer to. So I guess that kind of qualitative research doesn't claim that we have some general answer to how something works. It's kind of part of the story by doing qualitative research. So I don't think, so my problem here is with quantitative research making claims that are a bit unjustified. So yeah, more than that, I don't really know. You know, but I mean, reading qualitative stuff, it doesn't say that this is how everyone works all the time. If they're exposed to this treatment, they will do this or that, right? In that sense, kind of, you're not saying that you are doing something that is so big in terms of generalizability.
Yeah, I guess the idea of having a plan of analysis before you start, you can do that in qualitative research as well. So I think you can achieve it, but I just wonder if you thought about how to go about to
Not really. So one of my best friends, who's actually in Göteborg right now, she's an anthropologist of science, studying how people use big data in Sweden. So she comes here for her field work, and I don't know. So we've talked about this for hours, and I haven't really understood how to kind of combine with what I'm doing with what she's doing yet. So to be continued, kind of. But it would be interesting to hear more about, like, if you have thoughts on how you could set it up for your studies.
I guess
there are some challenges. Yeah.
forking must be available there as well. How should you interpret the data from your?
But they don't end up with a p-value that they.
No, of course not. Arne?
Your results are somewhat pessimistic, I guess, about what economics produces and what we do. But have you looked at how the results vary by this type of questions you pose? I mean, if there are very subtle nuances about human behavior, it might be easier to get it wrong than if you do an experiment on the impact of a tax on petrol or something, which we used to do in the good old days. I mean, have you looked how these results vary across the kind of questions you ask? If you have a very subtle psychological dimension you want to get at, it's much harder to replicate it, and get it right, I assume, than if you have a very simple economic traditional question.
So that's very interesting. I mean, with the sample sizes we have now in terms of how many studies we replicate, we haven't really been able to dig into subfields and say, what does it look like in the experimental papers in economics, for example? Because we have 18 papers, we cannot really say anything about differences in subfields there. So as I said, for psychology, there was some evidence that some of the social psychology experiments were less likely to be replicated than the cognitive psychology. But again, sample sizes are so small that I think kind of we need to continue with this, and then in 5 years we basically might have enough replication studies so we can actually say something more interesting than what we can say right now. So this is like a long-term project by many other people and me, basically.
But your hint is that we probably know quite a lot with quite high precision, even though some studies are hard to replicate. Is that?
Yeah, I think a lot of things we say as economists are true.
one observation of that. That's good, yeah. Yeah. Okay, we have one final, maybe. Yeah.
So when you present this to the business side of the world, what are their views on this? I mean, for example, when you look at it from a psychology perspective, and this is actually advice that they're going to give people, and medications are going to be written on this research and so on. So do you see any changes from that side based on these replicability issues?
So I actually haven't talked to any business side on anything, so I don't really know.
So this is the first exposure.
Yeah, but it would be interesting. I mean, I talk to people at the big pharma companies, for example, I mean, who end up with all of this irreproducibility. I would like to know more, kind of what's going on. I don't know if they would like to share that with me, but I would be very interested in that. And then just in terms of, okay, I talked to some kind of business leaders who are interested in like leadership courses and stuff, basically based on power posing, and then I kind of express my skepticism about the fantastic effects you can get from power posing on behaviors and hormones. So that's about it. I wish I had more kind of conversations.
Okay. Elliot, that was the last question. So thank you for an extremely insightful and important question. So thank you so much.
Thanks.